Hi, welcome back to a new episode from Data Privacy with Machine Learning. In this third section, we're going to be continuing sublines that we have established in the beginning of this series. First, we'll look in depth about the concept of differential privacy based on query principle. And then we'll be looking in details about the mathematical framework. Following that, discussion on the technique for two different types of values, either continuous or categorical type of data. And finally, we'll be looking at the lab illustration on the concept. So just to remind you one more time, we have set up the assumption in the previous episode, and here I would like to tell you the first introduction of this differential privacy subject. I want to assume the first type of scenarios that the data is queried. In this case, we assume like the data owner trusted actually the creator to have the data in their own premises, and the creator allow kind of query on this data set. So we'll carry on with this assumptions before we further talk about the second one of sharing the data set. Now, let me tell you that differential privacy happened to be the most prominent presentation when speak about privacy with data. And the reason, because of the mathematical presentation of such a framework. Now, before we discuss that, I would like to speak about the fundamental laws, which actually have been discussed previously, but nothing to be learned about the subject when the data is released. This is what we aim for. We want to make sure that we learn about the population without actually exposing privacy of the individuals in that data set. Well, that is possible or not possible. That was the discussion of the entire field of research. Now, the differential privacy have come with a very interesting outline. Says, well, if we consider the data as a resource, then we can actually establish some kind of a mathematical representation of the problem. And what does that mean, data as a resource? It means the more the information you learn from the data set, there is more privacy will be used up, which actually kind of makes sense. The more you learn about the population, the more you are more likely to learn about individuals in the data set. The foundational ground in relation between differential privacy and machine learning in particular is a framework. It says that the goal of differential privacy in machine learning is to design this kind of algorithms that can actually train models on type of data that we call private data. And this private data, it has certain attribute that the privacy was integrated into their values, while we are providing measurable guarantees of privacy. This ensures that the algorithm do not memorize sensitive information about the training set. As we have said before, one of the drawbacks discovered over the time with differential privacy that perhaps when it works with machine learning, still the AI models still can memorize some sensitive information. Maybe I will be able to show you some examples to illustrate what does that line mean in particular. So this is what we are actually trying to sit at a fundamental ground of understanding the framework of differential privacy at the first place. Now, the mathematical intuition of differential privacy, as I have mentioned, it make it a quite a bit prominent and promising kind of a direction that research can go for. To understand the math of differential privacy, which I see it personally from mathematical perspective, is not complicated at all, but rather a little bit ambiguous in some of the terminology. I don't know the reason why that happened, but I think that the research took off, the directionality was not completely established. That perhaps explained the ambiguity about mathematical presentation, although it is really simple. Now, I want you to be familiar with some of these terminology like this delta F and then these D and D hash. Now, D here represent the data set. This is what we are working for. We have a data set, and D hash, we call it a neighboring data set. So you have these two data sets, and there is this max. It will have representation in a while to be understood, but there is like a kind of a maximized value will be taken off from this D, lead to the outcome of this D hash. And then we do a difference between these two data sets, which we call it one data set, and the other data set happens to be a neighboring one, we call it. But actually, if you remember our examples in the lab when we illustrate linkage attack, we have this telecommunication company data set, and then we have this Techqniques company. So the Techqniques is the D hash is the telecommunication. So we have these two data sets. And then we do some difference between them, and that will lead us to this delta F. We will understand it in a while. Now, in many books and research papers, they refer to this delta F as a sensitivity value. I will show you mathematically it has its own name as well. And then we have the second part of this equation represented with this PR of a certain value divided by another PR. PR here, the probability. Now, what kind of probability we're looking at? We're looking at a result returned when we query this data 1 and result returned when we query data 2. A here, it represents the function we apply. For example, in our previous episode, we spoke about scenarios when we query the data set about age, for example. Now, when we query, we say, what is the average age? Now, average here represent the A, or the function. Now, in many books and tutorials, they refer to it as a mechanism. So I want you to be familiar, either as A function or as M mechanism, they all the same. Refer to the function we apply or the exact query that we are actually requesting. And S here represent the result that is returned. In our previous, again, lab example, before we applied anonymity, the query was returning a subset of 2. Now, when we apply the anonymity, the S or this subset returned from the query, it was like 10 cases. So this is the meaning of S. And then we are saying that there's this ratio have to be less than or equal to e to the power of this epsilon, a Greek value. Now, this epsilon, it is really a huge ambiguity about the entire math of differential privacy. I will explain that in the challenges about the framework of differential privacy at the end of this episode. But for now, it has also its own name. We will look at it in a while. So these are the actual two mathematical representation of the problem of privacy when we speak about the framework of differential privacy. I will just remind you the word M represent mechanism in many books and training materials. In the function I have brought here from a different reference, it was A. So either A or M or even just F as a function, it doesn't matter. I want you always to know that represent a mathematical function anyway. The query when we ask about average or counting or max, it's actually the meaning of M or A or the function itself. Let me show you in details some intuition about this mathematical function. Let's just start with this delta F. What does that mean? Now I have this snapshot of two different data sets. And this I quoted from a training material. I will put it up in the reference if you would like to check that out. So here we have the first data set that contains some name and age, and the second data set. So in the original data set that contained name and age, I have done something related to this max between D and D hash. So what happened, I looked up the largest or the maximum value of age in the original data set, which happens to be age of 52. And then I remove that. Once I have done such action, then I would have like a new data set without this maximum value. And that's exactly the representation of this max between D and D hash. It means remove, for example, in this case, the largest or the maximum age happens in the age feature. Now, when you subtract the differences between these two data sets, in this case, the first we call it the data set, the other one called the neighboring data set. When you find the difference between both of them, that will lead you to this value of delta F. In many books, it's referred to as the sensitivity. Now, mathematically, I have to tell you, this is not actually nothing but it's calling the Hamming distance. And Hamming distance in generally try to find out the difference between two entities. In this case, the entity represents actually a data set. Now, if let's say I have counting function and I have averaging function. Now, in the counting function, before in the original data set, we have 9 entries. But after I removed the largest age, the whole row was deleted, I have a new data set, but this time the counting, it will be 8 entries. Now the delta F, in this case, it will be 9 minus 8, that is only 1. However, if I am applying an average function, first original data set, the average of the age was 35.3. However, in the new data set, after I have removed the maximum age value, it turns out the average to be 33.3. The difference between them happens to be 2. Here, the delta F is 2. So in one function, the delta F is 1. In another function, delta F is 2. This is how the sensitivity or the delta F is calculated. I have to give you this intuition because depends on that delta F, we will actually try to add that kind of noise we've been talking about related to differential privacy at the first place. Now, if we want to just put this in much more syntax of wording, differential privacy provide, as we said, a mathematical framework to quantify and to control the privacy guarantee of a data analysis system. In particular, it is defined in terms of this parameter called epsilon. I've shown you in the second equation, which represent privacy budget or the level of privacy protection provided. Now, this is a very nice definition. It sounds so good and so clear. In fact, it isn't. And one of the challenges, nobody really understands what does actually this epsilon exactly mean. That it seems to be related, decide on the level of privacy can be revealed or not. This value of epsilon remind me in the AI framework and machine learning when we were actually trying to create this derivative function in the back propagation. We were trying to work on something called learning rate. Now, mathematically, we know what is learning rate. We can show it. That is the amount of learning in every propagation round we do. But in this case, epsilon, one of the challenges differential privacy faces is actually to explain what this is exactly mean. But I would try my best to put this in way clear terminologies as much as I can as we move forward. Now, here is the second part of the equation that we have seen. We have these two terminology. It's a ratio, right? So the probability of getting this whatever mechanism which we here written as an A or in the text written as an M mechanism. In this case, like the average function or the counting function. When we apply to the dataset, the original one, the dataset returns a result, which is actually a subset, right, from the original dataset. Now, what we want to take the probability. If I do change on the dataset, we will have this neighboring dataset. And I equated it. It returned to me again a subset. What we want, different ratio probability. This first subset defined by the second one should be less than or equal to this e to the power of epsilon. And epsilon, as we said, it's a huge discussion. This is the mathematical aim that's trying to be proven along the line. Maybe this particular equation will not be used in any way, but only to explain the mechanism of differential privacy. So what I have decided to do is to bring this into a practical application where you can really understand, grasp the meaning of it. Before I take you there, I would like to discuss an important things about the threat models for differential privacy. Because whatever mechanism or technique we will apply for differential privacy, we have to consider an important scenario. If I would have to choose the scenario of trusting my data with the creator, and I take the creator's word that my data is private and will not be misused. But the question is, what if the location of the creator server has been hacked? It means that data has been compromised. To this end, there are different threat models you have to take care of or to consider while you are actually designing a privacy framework for the entire workflow that you are proceeding with. Now, the first type of this kind of a threat model is called a central differential privacy. Basically, as we said, the data owner trusts the creator, and then the creator has to consider, what if my server is hacked? I want to make sure that the data or the privacy of the data shall be preserved. Now, the second one, it's called actually a local differential privacy. In this case, the data owner trusts nobody but only their own premises. It would do whatever technique of differential privacy needed in their own premises. So they will not actually rely on the word by the creator. And the third type of model is called the hybrid one. As the name implies, that sometimes maybe depends on the sensitivity of the feature. Some of the data you still can leave it for the creator to take care of, but if some of the features are really highly sensitive, in this case, doing the privacy part or differential privacy technique in your own premises. So what we want now to start actually applying this differential privacy, as we said, adding noises. I have decided to explain that depends on the type of the data. Now, for continuous type of features, take an example like age or salary. We want this age, say it's 40. I don't want to say exactly 40. I want to add noise to this number, which will cause a kind of a privacy preservation to the real value. This is the simplest idea. The question is, instead of saying 40, I could say it's 40.25 or it's 39.78. So there is this difference between the original and the one I am reporting. It's called the noise that I have added. Now, how to do that kind of noise? It's not just a random behavior of adding any numbers. Why? Because you want to make sure whatever noise you add, still you preserve the real value of 40. It's still encapsulated there. Not 100%, but at least as close as possible to the 40. Why? Because we need to make sure the outcome of whatever reason the data is used for still preserved to be efficient. Now, to draw the noises, basic idea is to use mathematical background of using one of those distributions. To understand the meaning of distribution, I would have to remind you again, refer to my third book, Prediction from the Start to the End. In particular, you must know unit, where I discuss all kind of distribution that you might need to use. One of them in particular called the Laplace distribution. There are other distributions, well, you may want to check them out, like the normal distribution, the Gaussian distribution, but seems to be the Laplace distribution in most of the literature proven to be will work with differential privacy. Now, before I tell you how this kind of distribution is used to add noise, I want to tell you about this Laplace distribution. So we have here the PDF probability density distribution for Laplace and the cumulative one, the CDF. Before I take you to the lab, I want just to draw your attention to an important thing. This Laplace distribution relies on two important parameters. The first one called the mu parameter and the second one called the B parameter. Now, the mu, if you have ever worked with normal distribution, it represents the actual average or the mean. In a standard kind of normal distribution, it used to be 0, and the B is the standard deviation in that kind of distribution. So it's a very similar idea. But here, Laplace distribution, it uses again mu and B, whereby in our case for differential privacy, we will always assume mu at value of 0. So we don't want to assume the average value of the accounting features. Now, what is B? It's the second parameter, which we have to understand right now. Now, in the literature, it's written as epsilon in some books. It said it's epsilon, other books say it is just B. But I have chosen to make it as simple as possible to understand Laplace relying on these two parameters. In our case, we will assume one of them always going to be 0, which is the mu, and the other one, which is B in this case, has to be larger than 0. Why? Because if we look at the equation for the PDF, it's obvious we divide by B, so we don't want to divide by 0. It's any value larger than 0. This is very important thing to observe. Now, if you know how to write this PDF and CDF in Python, you can actually graph this on your own. Let's go ahead and check the lab just to show you the representation of Laplace distribution in Python code. So here in the same class that we have discussed before, the privacy class, I have another function which I call the Laplace function here. if I would actually take you to that function in particular, you could see I just written the PDF and the CDF. That's it. And then I would have to accept number of epsilons or B values. And based on them, I just graph or plug in the PDF and the CDF. And if I run this function, actually, I would end up with the two graphs that we have seen just now. These are three different values of B at 0.2, 0.5, and 0.8. Now, how to read this PDF and its relation to CDF? The CDF, it calculates actually the area under the graph. I mean, how much probability that value would happen. But let's focus on the PDF. We have seen the function just now in the slides. It seems like when I am working with the value P of 0.2, the tail of this graph seems to be so much sharp. And by the way, part of this, this is a kind of symmetric. It's just exponential distribution, which is another type of distribution. So it's a flip-flop of the two exponential distributions are separated by this line. But anyway, what interests us is to see if I move from 0.2 to 0.5, I want you to see how much this tail is snapped down and the edge of the tail seems to be went wider. And then if I change again to 0.8, I would end up with this green line. So what you can understand is it turns out this B value, or I written it here as an epsilon or B, whatever value, it seems to control how much the shape of this distribution would look like anyway. Now, this is the PDF. If I plug in 0, I would end up with this 2.5 or so. If I plug 0.5, I would end up with this value here. What is the CDF says? And I want to see the probability of having like any value less than 2. This is called a cumulative distribution value. You could see if I would have to draw here all the area under this curve, I mean the blue one or the green or the red, it's almost 100% chance I will get any value less than 2. Then 1.5, it will be around 95%. And if I am at the 0 here, it will be just only this area here. It's around 50%. So that's exactly the representation here. So from 2, you are almost at 100%. It's 1. If you are at 1.5, you are very close also to 95%. And if you are at 0 here, you are almost at 50% or so. So this is the meaning of this CDF and how they are related. This is the plus distribution. And this is the actual graph based on the two parameters we said. Mu always will be 0, but B, which we understand now from this graph, what effect it has. Now, what's the relation between this and the differential privacy is exactly what we'll find out in a while. So I'm back here to where we have stopped. We want to see the relation between this delta F, we have just learned how to calculate the sensitivity, and this Laplace distribution. Well, it turns out that whatever delta F I have depends on the function or the mechanism, as we said. If I take that value that I have calculated, the sensitivity, and I divide it by the assumption of epsilon in the original distribution. For example, here in this graph, I have chosen this original value of B in this case, 0.2 or 0.5 or 0.8. But in this case, what I want to do, I will calculate that by taking the actual sensitivity from the data set and divide by this value. And the new value I get, I will call it the actual B. So B here, it will not be the value I assume. It will be actually the value that is sensitivity divided by what I assume. That's why I'm saying this epsilon, which I call a budget value or budget privacy or whatsoever. It's as well ambiguous thing and terminology, kind of jargon somehow. Actually, the math behind it is just that one. This epsilon is the original B that was actually in Laplace distribution, but now we are bringing the idea of differential privacy. We want to link them. So if you take like differential privacy of 1, let's say for example here 1 in a counting function, 1 will be divided. If I go for 0.2, I will get 1 divided by 0.2, I get 5. So it means now B here will be 5. So it's as large as 5. If it's 0.5, it will be 2. So here B will be 2. You will see later on there are so many assumptions of this value of actually final B, because you have to see now how you count for this divided by whatsoever the original value. In Laplace distribution, the value was just between 0 and 1. So it's why 0.2, 0.5. But when we speak about differential privacy, you will see the value of B here change to be as high as 5. In some actually calculation, it goes as high as 20 as well. And as small as maybe 0.2 again or 0.5. So this is the ambiguity here. But somehow it worked. So what happened now, if I have this B and I know how to calculate my delta F, I can just get a value. And this value will be the noise will be added because already I have the X, which is actually the vector feature or the input itself. If it's an age, for example, say if I have age of 40 and I want to add noise to it. So if I take 40 minus 0, which will always get the same value. And B happens, for example, to be 5. We know how this 5 come from where, or maybe 3 or 2. And then you take the exponential of that, and then 1 divided by, again, 2 multiplied by 3, 2, or 5. And you will get this small value. This value, it's called a noise. And then you add it to the 40. This is the procedures of adding noise in general for a continuous kind of value. Maybe we can look at the lab example actually to illustrate adding noise to the age feature that we've been talking about. So if I get back here to my same exact class that we've been talking about, and maybe I activate the next function, which in this case, we call it query function with added noise. Now here, in this case, I will just follow the exact procedure I've been talking about. There are 2 noises. One I will add for a mechanism of average. The other I will add for a mechanism of counting. In either way, it's the same exact strategy. So if we go to this function in particular, you could see here, I have an average of the age, the normal age feature, and then I remove the maximum age as we discussed to calculate the sensitivity or the delta F or the Hamming distance anyway. And then what happened actually, if I take the difference between them, I will have this sensitivity or delta F. And then I will divide whatever it is by the suggestion of epsilon, which was the original value of Laplace distribution. Then now I have my B value. And once I have my B value, I will just proceed with the exact same function. Let's actually apply this to 2 different mechanisms, we said average and counting. So in the illustration here, the average of the age before any noise, it was around 60.83. And now if after I remove the maximum age, which happened to be 95 in this data set, the average age happens to be 60.51. So the difference between them happens to be the sensitivity or the delta F, which is 0.317 for averaging kind of function or mechanism. Now the B value in this case, it will be 0.317 divided by the epsilon. In this case, I assume it is 0.2. You can change 0.5, whatever. Then you will get this B value of 1.5. Now, if I have 1.5, what I have to do is just to provide it to the Laplace distribution, and then I will get a noise. And once I get that noise, I will add it to the average, which in this case, it will be 61.64. So the original was 60.83. Now it is 61.64. In other words, to say when I return the query result, I will not say it's 60.83, but I will report it as 61.64. And it's not random because this value or noise added based on the sensitivity level that we calculated and the epsilon that we suggested. If you change this epsilon to 0.5, you will get a different result anyway. Same thing for the counting, if I follow the same procedures. So the count was absolute of 299 subjects I've contributed to the data set. But once I added the noise, I could return, instead of 299, it just will return 292. So there's quite a bit difference here, but that again related to the epsilon value we are suggesting. The next thing maybe we need to talk about if the feature happens to be not actually numerical but categorical. In this case, we use a technique called randomized response. And randomized response was not exactly born as a technique with differential privacy. It has been used for a long time in different kind of research, especially kind of qualitative type of research. Now, the basic idea is actually to add noise. Don't forget, it's what we want. So we need to concern the idea of plausible deniability For example, if one of the features is to ask the subject whether there is a bad habit they are practicing to use, and you expect, of course, the subject won't feel so comfortable to tell you the truth, yes or no. To this end, maybe you can use this randomized response to tell the subject your answer is protected if I guarantee you plausible deniability. Yes, you will provide me with answer, but I don't want to say 100% his answer is this one, either yes or no. I want to say, well, there is a chance that 75 or 50% chance that his answer is real. And how to do that? You can rely on some kind of condition. The tool here could be a coin or a die or any similar of that kind to apply it. For example, one of the practices twice. So basically you tell the subject, I want you to have a coin in your hand and you have twice to apply them. In the first coin you flip, the result could be head or tail. Now, if it is head, I want you to write the answer truly for the question. So you're just going to answer truly. That means the second flip of the coin, which you are mandatory have to do it, it doesn't matter anyway because you will tell the truth. But imagine in the first coin happens to be a tail. Now, in the second coin, you are going to decide again. If it is head, you will tell the truth. If it's tail, you will not tell the truth or whatever answer you want to say. In this case, what happened actually mathematically, because 75% chance that the answer I have, it's actually true. How 75%? If you look at the start, we said there are 2 rounds. In the first round, you get head or tail. And in the second round, once again, you might get head and tail. We have 4 possibilities. And anyway, in the first one, in the left-hand side, if it's head, it doesn't really matter because he will always tell the truth. So this is 1. And the second one, either head or tail, as we said, the chances is going to be counting twice. So in this case, we have a 3 out of this possible 4 kind of outcome. That's why 3 out of 4 is 75% chance that the result that I have actually is real true. Now, this case happens very well with the binary kind of level, like yes, no question. But how about multi-level? If there are like 5 different answers. This way we use a different kind of techniques, which actually still a kind of improvement of randomized response. I will not discuss this particular kind of like multi-class cases in this training program, but you may check that out on your own. Now, the next thing we want to talk about is related to some subject with a workload of queries. Meaning to say, well, usually we answer to one counting query with one value, but we are often interested to learn much more about the data set than just only a single summary statistics. To this end, the collection of prediction or counting query called the workload, which support richer, of course, kind of analysis. Let's look at this example, say how many people, for example, have 130 serum sodium this month. So here we have like a kind of a load query because there is a serum to investigate, there is a time or a month to investigate. Maybe I could query another value of the serum, like 136. But if you look at the third question, we are asking about serum in general. So it seems to be overlapped with the first 2, since we are asking a general question. This is called a workload kind of a queries. So our goal is to design this kind of mechanism that answer every query in the workload while providing a low or ideally minimum expected error of noise. Because every time you are adding noise, it will be added in the next and the third query. So you will have a large noise then. So one of the techniques says, or the mechanisms applied, to repeatedly apply Laplace mechanism for each query independently. But an improvement on that happens is to first actually compute the histogram of the serum sodium in this case, because we are talking about this feature. Then we estimate the cumulative counts by adding up adjacent cells to the noise histogram. There's one drawback of this technique. It's the noise introduced in each histogram cell can accumulate, as we said. And then I sum or aggregate all these noises, but it can really go large and affect the efficiency. That's why an improvement to that could be conceptually as a middle ground between the 2 cases. So the idea is just to invoke the Laplace mechanism on a carefully selected set of queries. In other words, to say, I will randomly choose from the feature, in this case like serum feature, and then from that subset I will generate that noise, and we consider that noise to be actually representative of all noises for any kind of a query within the workload itself. Now there are two open source tools that you can check on your own. Both of them provide variety type of examples and much more explanation on the subject of workload queries in particular. The second also scenario is to query across multiple data set. Now, if you look at this graph you see in the screen, imagine you have this three individuals like Jane, John, and Sally, and they happens to be within a certain table called the workers table. And then I was recording jobs or tasks that's been assigned to each one of them in a different table. Now, basically here, from a single table perspective, Sally is only one entry. But when we link Sally, which happens to have the probability to actually accomplish multiple tasks, it means it will have like two entries in the employer table. Now, if happens for any reason, I want to actually delete or remove Sally from the workers, that means I have to delete two entries in the jobs, and that will affect the result anyway when we make join kind of query. To this end, if Sally has three jobs, that will have an effect or whatsoever. So the sensitivity of this kind of query is bounded by the maximum number of jobs that the worker, in this case, can actually take per year. This is one of the most important part when it comes to query access from multiple data sets. Once again, I'm not going to discuss this in details anyway in this series because I will leave different sources that you can check on your own. But there are two open software tools. Both tools actually discuss also in much more details about some of these kind of queries across multiple tables. Now, that was the end of the session, and we have left with the fourth session, which is going to conclude the entire idea of differential privacy anyway, with much more practical examples, giving the second scenario of a shared data set. That's exactly what we're going to do next. I will see you then. Cheers.